Hello, everyone. Welcome to this presentation about Pareto compliance from a practical point of view. This research was done at Universidad Autónoma Metropolitana, Unidad Guajimalpa, and my name is Jesús Guillermo Falcón-Cardona, and my co-authors are Saúl, Zapotecas-Martínez, and Abel, García-Nájera. So what's the agenda for today? We have a brief introduction to some basic terms, then I will explain you what's the practical point of view of the use of Pareto compliance, that is a very interesting property of quality indicators, and then I will explain you our main results, and we will have the final remarks for this research. So let's go for the introduction, the Pareto compliance, and some other things. We have to go to the basics. In this case, the Pareto dominance. Pareto dominance is a very well-known binary order relation that we commonly use in multi-objective optimization. We have the strict Pareto dominance, weak Pareto dominance, and the strong Pareto dominance. We can see here an example of the use of this strict Pareto dominance, where A strictly Pareto dominates B. We also have that A strongly dominates D, and finally, we have that A weakly Pareto dominates D, B, and C. But what's the idea of this binary order relation? We can use this Pareto dominance to order points that live in an objective space. And that's the idea of having this picture, sorting the points as we do in the non-dominant sorting. And well, now we can also use the Pareto dominance to compare sets. Let's remind that multi-objective evolutionary algorithms produce approximation sets. That is, some solutions that approximate the Pareto front. So we can use the Pareto dominance to compare these approximation sets using the weak dominance, the strict dominance, that it's the one that we are very interested, and also we have the strict element-wise dominance, the strong dominance. So the question here is to be or not to be Pareto compliant. Let's go to define the Pareto compliance. We need a quality indicator that assigns a real value to one or more Pareto front approximations according to some quality aspects. In this case, we will use the convergence indicators, and using these convergence indicators, we will define the Pareto compliance, the weakly Pareto compliance, and the not Pareto compliance. So let's assume that A strictly dominates B, and an indicator is Pareto compliant if the indicator value of A is strictly better than the indicator value of A. That's the idea here, is that this indicator can reflect the order structure of the Pareto dominance extended to sets. Also, we have the weakly Pareto compliance, that is, the indicator value of A is less or equal than B, the indicator value of B. And finally, if the indicator cannot reflect the order structure of this strict dominance, so we have that the indicator is not Pareto compliant. So we have also the three IGDs, IGD, IGD plus, and the newly defined IGD plus plus. In this case, IGD measures the average distance between a reference set, we have it here, to the approximation set A. But the bad thing here is that IGD is not Pareto compliant. We have the IGD plus. IGD plus is weakly Pareto compliant, so we are kind of happy, not so much, but we have a single modification to IGD. And also we have IGD plus plus that requires the IGD plus and also the hypervolume indicator that we know is a Pareto compliant indicator. So using an order preserving function, in this case the augmented Chebyshev function, we have a kind of fusion as in the Dragon Ball Z anime. So we will define a Pareto compliant indicator, the IGD plus plus, that uses IGD plus and the hypervolume indicator and also the order preserving function to define this Pareto compliant indicator. So we are we are very happy in this case. So what's the importance of Pareto compliance? We have here in the picture a reference set, an approximation set A, and an approximation set B. And we know if we look at the coordinates, that A strictly dominates B. So if we use IGD, which is not Pareto compliant, we will know that B is better than A according to IGD. So it's kind of a misleading conclusion. Regarding IGD plus, we know that IGD plus, the IGD plus of both approximation sets are equal. So IGD plus cannot decide which one is the best. And finally, the hypervolume indicator, which is Pareto compliant, effectively reflects the order of the strict dominance. So that's the importance of a Pareto compliant indicator, not producing misleading conclusions when assessing a Pareto form approximation. Another use of quality indicators, apart from assessing Pareto forms, we have the design of multi-objective evolutionary algorithms. So we can define the indicator-based MOEAs, the IB MOEAs. And we can use indicators to define the environmental selection, a density estimator, an archive, and also the mating selection. And according to the preferences of each indicator, we will have different distributions reflecting these preferences. So the quick question here in this research is, what's the effect of a Pareto compliant indicator? And we have two types of utilization: performance assessment and the guide of evolutionary process. So regarding the performance assessment, the effect is not contradict the Pareto dominance extended to sets, and also we have the possibility to define good conclusions using these Pareto compliant indicators. But in the case of guiding an evolutionary process of a MOEA, we don't really know what's the practical effect of this Pareto compliance. So the idea of this research is to define what's the practical effect of Pareto compliance. Okay, so to define a fair comparison between IGD, IGD plus, and IGD plus plus, where we have not Pareto compliant, weakly Pareto compliant, and Pareto compliant indicators, we will use this general framework of a steady state MOEA. This general framework is completely related to the one of the SMS MOEA. So instead of using the hypervolume contribution, we will use the contribution to IGD, IGD plus, or IGD plus plus. So what's the idea of this algorithm? We will generate a single offspring solution. Then we will execute the non-dominant sorting using the Pareto dominance. And then we will use an archive. This is a very important thing to try to promote a good distribution of solutions and to define the reference set, which is necessary for the calculation of IGD, IGD plus, and IGD plus plus. Okay, so then we will generate the reference set using this archive. So that's the importance of this one. And finally, we will execute the density estimation using the IGD, IGD plus, and IGD plus plus, and also the archive previously defined. So the archive is a very important thing here because we will generate a good reference set. In this case, it is based on a recess energy, which is a very interesting function that comes from the physics, from the potential theory. And the idea of recess energy is to promote uniformly distributed solutions independently of the Pareto form shape. So we have here the interaction between molecules and the idea to discretize a surface. So the idea of our archive is to define the Pareto dominance as the main selection criterion, and in case that the archive size is exceeded, we will execute an elimination process, a backward elimination process using the recess energy. So this will ensure the generation of a uniformly distributed solution set. Okay, so this is the basic idea for a fair comparison, but what's the experimental design? We will compare the effects, the practical effect of IGD, IGD plus, and IGD plus plus when they are embedded into a many objective evolutionary algorithm. So we will define the IGD plus plus MOEA, IGD plus MOEA, and IGD plus IGD MOEA. And the question here is, what's the practical effect of Pareto compliant quality indicators? To this aim, we will use multi-objective optimization problems from the Lamé superspheres benchmark, and we will have the Lamé problems and the mirror problems, the ones that are inverted, using different values for the gamma parameter that defines the Pareto form shape. So having highly convex, convex problems, linear, concave, inverted convex, inverted concave, plenty of shapes. And the idea is to define a classical performance analysis, using the hypervolume, the diversity indicator, in this case, the pure diversity, and we will assess the final Pareto form approximations produced by these three algorithms. But this is not so new. The important thing here is the online performance analysis. In this case, we will have a waveform correlation. We will define a convergence graph during the whole evolutionary process, and we will compare these waveforms of the convergence graphs. This is the main thing here for the comparison purposes of our research. And well, okay, let's go for the results. For the results, we have the classical performance analysis, where we compare the final approximation sets. We have the summary of our results using the hypervolume indicator and also the pure diversity. And we have here some bar plots where we define the first place, the second place, the third place. That is the rank that each algorithm got in the comparison. And according to the hypervolume, we know that IGD++ MOEA is the best algorithm. So it outperforms all the other ones. But in contrast, for the pure diversity indicator, we have a more balanced comparison. We know that for the first place, the three algorithms share the same number of test instances where they were ranked first, and also for the second, the third place. So we have a kind of a balanced comparison, but comparing the Pareto form approximations produced by these algorithms, we can see here that IGD MOEA that is using a not Pareto-compliant indicator produces very good Pareto form approximations with uniform distributions independently of the Pareto form shape. But in contrast, the IGD++ MOEA, which is Pareto-compliant, has some problems. Let's see this Lamé problem, which is convex. IGD++ cannot cover completely the Pareto form. This is the same thing for this problem where it has some empty spaces. So in comparison with IGD MOEA, it is not so good. But the classical performance analysis tells us that IGD++ MOEA is the best. But according to the distribution, we have some doubts about this conclusion. So the classical performance analysis is concluding that Pareto compliance makes a big difference when assessing the final quality of Pareto form approximations, but we have an insight that is that's not true. So we have here the online performance analysis, that is the similarity between waveforms. So we measure the hypervolume quality of the population all along the evolutionary process, and we define these convergence graphs, these hypervolume-based convergence graphs, and we measure the three convergence graphs for a given multi-objective optimization problem using the cross-correlation measure. So we have a value between -1 and 1. So if it is closer to 1, we have a very good correlation, but instead, in contrast, if we have a cross-correlation value closer to -1, we have an inverted correlation, a negative correlation. So using this convergence graph, this online analysis of the effect of the Pareto compliance, we can also define what's the gain that each algorithm produces according to the hypervolume. Okay, so in this picture, in these figures, we have the online hypervolume plot, the online pure diversity plot, but the hypervolume gain plots tell us that it's not so different the gain between the algorithms. We can see that the order of gain is very small. So even though that IGD++ give us the best convergence behavior, it is not the same when we compare the whole evolutionary process. And there are some cases where we have that IGD MOEA, which is not Pareto compliant, in fact have some hypervolume values in contrast to IGD+ and IGD++. So based on these convergence graphs, we can see that there is no big difference between using a Pareto compliant indicator and not using them. For example, the IGD and IGD+, which are not Pareto compliant and weakly Pareto compliant. So everything is not that bad according to the Pareto compliance. We also can define the speed of convergence. But regarding the speed of convergence, we can see that IGD++ MOEA has this speed is very good in convergence. So the speed of convergence of this IGD++ MOEA is better than that of IGD MOEA and IGD+ MOEA. But we can also see here that the difference is not that big, because the Pareto form approximations of IGD++ MOEA are not so good as we discussed previously. Okay, so based on the online performance analysis, we know that the Pareto compliance does not make a big difference during the evolutionary process, as in contrast to the classical performance analysis, where the Pareto compliance is very good. But for the whole evolutionary process, the Pareto compliance is not that important. Okay, finally, the conclusions. So first, Pareto compliance is critical for assessment of Pareto form approximations, but in contrast, is not so critical during the whole evolutionary process, so our heart is broken. Also, we have the Pareto compliant indicators slightly speed up convergence, but they have some problems. And finally, no matter the Pareto compliance, all indicators can cooperate to produce better Pareto form approximation. So this is the future work. We can cooperate, make a cooperation between all these algorithms to produce better Pareto form approximations, depending on some stages of the evolutionary process. So thank you very much for your attention. Thanks to the audience and to the GECCO.